Will the history of astronomy be divided between before Webb and after Webb?
Yes, I believe it will be.
So something real is happening, but we can't tell yet if it's a mistake in our observations, a mistake in our interpretation, or just something nature is surprising us with, such as a new kind of dark matter, a new kind of dark energy, or something else that would be really exciting to discover. So if there's a Nobel Prize in here, that could be one of them.
Look at this image. It showcases a newly discovered early galaxy that existed approximately 13 billion years ago. Researchers are astounded to find that this galaxy is significantly more massive and mature than anticipated for a galaxy emerging from the so-called infant universe shortly after the Big Bang. This discovery highlights a pattern. The Webb telescope has consistently identified such unexpectedly advanced galaxies in the early universe, challenging our fundamental understanding of cosmic evolution. Since its launch, the Webb telescope has been pushing the boundaries of our cosmological theories. Its remarkable capabilities have brought forth groundbreaking discoveries, and the latest observations point to a concerning revelation about the very nature of our universe. Recently, astronomers, including Nobel Prize-winning physicist David Gross, have stated that the Webb telescope has confirmed serious discrepancies in our previous understanding of the cosmos. This isn't just about the identification of larger or particularly bright galaxies. Rather, new data from the Webb telescope has questioned long-standing cosmological models that we believed were robust and reliable. To delve deeper, one of the fundamental tenets of cosmology is the assumption that the spatial distribution of matter in the universe is uniformly isotropic. This means that when viewed over vast distances, the universe should appear the same in all directions. This assumption has been a cornerstone of cosmology for over a century because the gravitational forces at play in the universe are expected to influence matter uniformly on large scales, resulting in no observable discrepancies in the large-scale structure that evolved from the initial conditions set by the Big Bang. Traditionally, scientists operating under this model have expected that everywhere we look, we would encounter a consistent density of matter, similar temperatures, and a planetarium of galaxies, all expanding at a uniform rate. The Big Bang model, widely accepted as the most coherent framework for understanding the universe's origins and evolution, is predicated on this idea of uniformity. Additionally, the cosmic microwave background radiation, leftover thermal radiation from the Big Bang, has long been interpreted as evidence of this uniformity across the universe. However, a recent study published on February 6th in the Astrophysical Journal Letters suggests that the assumption of isotropic expansion may be fundamentally flawed. Astronomers have identified that the universe is not expanding uniformly. Rather, the rate of expansion varies significantly depending on our observational vantage point. This revelation poses a critical challenge as it disrupts the established consensus among astronomers regarding the current estimated age and inherent nature of the universe. David Gross articulated this shift in perspective, asserting that this situation should not merely be termed a tension or a problem, but rather a profound crisis in cosmology. To fully appreciate the implications of this revelation, we must revisit historical foundations, such as those laid by Edwin Hubble in 1929. Hubble provided the first substantial observational evidence for the expanding universe, using the largest telescope of his time to demonstrate that the farther away a galaxy is, the faster it appears to be receding from us. This pivotal discovery led scientists to the conclusion that the universe must be undergoing a uniform expansion, which in turn implied a finite age for the universe itself. In light of these recent findings from the Webb telescope, the validity of this uniform expansion model is under serious scrutiny, prompting a re-evaluation of the very fabric of our understanding of cosmic development. As astronomers continue to analyze these new data, the quest to reconcile our theories with the observable universe may lead to revolutionary shifts in our comprehension of cosmic history and the universe's ultimate fate. As the expansion happens uniformly across the universe, accurately identifying the expansion rate known as the Hubble constant allows us to reverse engineer the cosmic timeline and compute the age of the universe. However, prior to the launch of the Hubble telescope, there was significant uncertainty regarding the universe's expansion rate, or Hubble constant. This figure is essential for determining the universe's age, estimating its development over billions of years, and comprehending the forces at play. With the launch of the Hubble Space Telescope, it became evident that the universe might be as young as 9.7 billion years or as old as 19.5 billion years. This younger age, however, posed a major issue as it would imply that the universe is younger than the oldest known stars. Over time, astronomers have employed various techniques to pinpoint the precise value of the expansion rate. Yet, surprisingly, these methods have yielded different results. It seems as though the universe is expanding at different rates depending on the observations made. Presently, there are two leading methods for determining the Hubble constant. The first method involves examining tiny variations in the cosmic microwave background, which is an ancient remnant of the universe's initial light produced approximately 380,000 years after the Big Bang. Between 2009 and 2013, astronomers utilized the European Space Ice Planck satellite to map this microwave background and infer a Hubble constant of around 67 kilometers per second per megaparsec. The second approach uses Cepheid variable stars, or supernova, as a reference for distance. As Cepheids brighten, their pulsation rate slows down, providing astronomers a way to measure their actual brightness. By comparing this intrinsic brightness to how bright they appear, we can determine how quickly the universe is expanding. But this is where the enigma begins. Based on Cepheid variable measurements, the universe's expansion rate is approximately 74 kilometers per second per megaparsec, which is significantly higher when compared to the measurements from Planck. Initially, some researchers believed that this discrepancy could be attributed to a measurement error. However, Adam Ree, a professor of physics and astronomy at Johns Hopkins University, recently stated that we have now covered the complete range of what Hubble observed, allowing us to confidently dismiss a measurement error as the explanation for the Hubble tension. Furthermore, the new images from the Webb telescope reinforce that previous measurements are accurate, indicating that the universe is expanding at different rates in various locations. This variation in the expansion rate suggests that the universe may not be uniform everywhere. If the recent findings are accurate, they could fundamentally challenge our standard cosmological model, which has long relied on the assumption of a uniform expansion of the universe. This model has allowed scientists to estimate both the age and size of the universe using a consistent value for the expansion rate known as the Hubble constant. However, variations in this rate, depending on the region of the universe, raise critical questions about our understanding of cosmic dynamics. A particularly intriguing hypothesis suggests that dark energy, the enigmatic force thought to be responsible for the accelerated expansion of the universe, may not be uniformly distributed. If dark energy exhibits greater strength in some areas compared to others, this could lead to disparate rates of expansion throughout the cosmos. Such a revelation would not only complicate our cosmological models, but also challenge the cosmological principle, which posits that the universe is homogeneous and isotropic on a large scale. If these principles are violated, we could encounter scenarios that defy conventional physics. For instance, just beyond our cosmological horizon, gravitational forces could react in unexpected ways, potentially reversing direction due to disparities in mass density, while the speed of light might vary dramatically, falling below that of ordinary walking speeds. Moreover, the realm of possibilities could stretch to the fantastical, such as the existence of mythical creatures like unicorns. The recent discovery from the Webb telescope has ignited a significant debate among astronomers, prompting a re-evaluation of established theories. The implications of non-uniform expansion threaten to disrupt the foundational concepts of astronomy, calling into question the applicability of physical laws as we currently comprehend them. As researchers grapple with these revelations, the very fabric of our understanding of the universe hangs in the balance. Thanks for watching. Share your thoughts with us in the comments section, and don't forget to hit the like and subscribe button for more thrilling information. Heat. Heat.